Streaming. We are streaming, everybody. Let me pull up my stream manager on my phone. Close that. And let's pull this over here. We're going to hit the 24th hour of the stream, everybody. No. Don't quit, Emacs. We're going to hit the 24th hour. And this is just my counter for where we are in the exercises. Yeah, by the end of today, we'll be at hour number 24, which is pretty exciting. So we've been doing this for a while. And I'm just probably going to do pen and paper all day. I might do a little bit of coding. We might do a little bit of coding. Also, my back hurts today, and I didn't have ibuprofen until like 5 minutes ago. But that should be fine. There's our stream manager. I wonder if it knows I'm live. I think it knows I'm live. So we were thinking about skipping exercise 13. That's what we were thinking about. I only had one ibuprofen. I was going to have a second one in like an hour, but I'm going to have my second one now. Because my back is really hurting me. Where's your ibuprofen? Prove that the union of three subspaces is a subspace of V if and only if one of the subspaces contains the other two. So we can prove that this isn't true for Z2, for Z mod 2. And I'm tempted to do that. I think that'll be fun. We can disprove it for Z mod 2. I'm going to number 14. Example 1.38. So let's verify this. U equals X in F4 such that, oops, wrong screen, XXYY in F4. XXYY in F4 such that X, Y are in F. and W equals XXXY in F4 such that XY is in F. Now we want to show that U plus W is XXYZ. Want to show that U plus W equals XXYZ in F4, XYZ in F. Hello, one viewer. How's it going? Thanks for coming to the stream. We'll see what song is stuck in my head this time. We'll see what song I'm whistling this time. I think it's the same song I was whistling last time. Well, we want to show that U plus W, so U plus W equals X plus X, X plus X, X plus Y, and Y plus Y is in U plus W. And this is as simple as observing that 2x, x plus y, 2y, there's 3 unique numbers. And those unique numbers can be constructed basically any way you want. So we're basically saying there exists an x prime such that x prime equals 2x. There exists a y prime such that y prime equals x plus y. And there exists a z prime such that z prime equals 2y. So I'm basically satisfied with that. X prime, y prime, z prime is in U plus W. Meaning U plus W is equal to the set of all x, y, z in F4 such that x, y, z is in F. And I feel like that's verified. It's a little sloppy, but I feel like it would be fine. It would be fine for math. It's not fine for like deduction for cock, but it's fine for math. So maybe we'll formalize this. $15, I guess. I'm going to have to heat up some coffee. I'm going to heat up some coffee. All right. U is, suppose U is a subspace of V. Then U plus U, but if I have set scalar where, if I have set scaling where 2A is defined, or we'll say KA is defined to be KA for A in A, then U plus U equals 2U. But 2U is also a subspace of V because subspaces respect scaling, or scaling is closed under subspaces. So 2U is like equivalent to V, to being a subspace of V, I mean. I think 2U, my posture. Come on, Q Doc. Posture, a little bit of stretch. Oh, someone's got to rub that out. Oh. I think 2U is also a subspace of V. But what if the point is that 2U is in the subspaces of 2V and not in the subspaces of V? Yeah, so if U is a subspace of V, then 2U is a subspace of V. Because U is closed under scaling, then linear combinations of, I mean, really it's linear combinations. Like 2U plus Oh, never mind. I think I'm satisfied with this. Let U V into U. Yeah, because of the closures, this is satisfied. I'm happy with it. I'm moving on. Is the operation of addition on the subspaces of V commutative? In other words, if U and W are subspaces of V, is U plus W equals W plus U? This is going to be a yes. Let me look back at the definition of plus to see how I prove it. So we're going to say, hold on now, exit, reset, exit. U, V are in the sub. U, W is in the sub spaces of V. Want to show that U plus W equals W plus U. So let me just go, I'm going to go up to the definition of plus. So it's a field law that addition is commutative, right? It's a field law that addition is commutative. There's something about streaming that makes it makes my internet slow. Yeah, field is commutativity of addition, right? So since addition's commutative, this is just saying left side equals U plus W equals U plus W such that U and U, W and W equals W plus U such that U in U and W in W equals W plus U equals right side. And that's all I'm going to do. Next song. I'm excited for the direct sum. For the direct sum exercises. Well, again, this is just. This is trivial. I'm glad associativity for addition and multiplication is in the underlying field. So Like, maybe if I do this, my clicking will be better. Yeah, I'm not even going to verify this. I know what this proof looks like. It's just a trivial verification. I'm glad that he pointed it out. Um, okay, so this is interesting. Now we're talking. This is going to be a good one. All right, we're definitely going to formalize 19. And 18 will get formalized, I believe, along the way. So what am I looking at? Does the operation of additional and subspaces V have an additive identity? Yeah, like I think this is I think the additive identity is the singleton set containing the zero vector. Um, for every U in subspaces of V, U plus the set containing zero vector equals U equals the set containing zero vector plus U. Ba-da-ba-ba-ba-da. Which subspaces have additive identities? It's not all subspaces. I want to Google this and see what people are saying, but I can't think of a subspace that doesn't have an additive identity. A subspace that does not have an additive identity. We're getting there, people. This is true, right? We don't need to show this. Consider the subspaces of V. Which U in subspaces of V have does there exist minus U in subspaces of V? I'm nervous, y'all. I'm nervous about this. STU plus minus U equals... Oh, wait a minute. No! I was going to be so wrong. Ah! It's not every subspace. It's not every subspace, y'all. So let's say I have x, x, y in R3. Say U equals, then minus U equals minus x, minus y in R3. And the entire U plus minus U it would include like 1, 1, 2. So if U equals ... comma 1, 1, 2, comma 1, 1, 3, comma ... then minus U would equal ... comma minus 1, 1, 2, minus 1, minus 3, comma ... U minus U would equal ... comma 0, 0, 0 for this minus this, but then it would be 0, 0 minus 1. For this minus this. So which subspaces have additive inverses I truly don't know. And then this would be 0, 0, 1, 0, 0, 0 again, which gets crossed out, dot, dot, dot. Minus u is not the additive inverse of u. Where's my mouse? In general. In general. Time for more coffee. We do a stretch. Oh. Oh. Oh, yeah, my back hurts. Just a little stretch. Deep, dee, dee, dee. Because even though it's a sum, it's basically a join. Like, you're drawing vectors from a join of the left and the right of the sum. Does that make sense? So the question is, which subspaces have an additive inverse? I mean, 0 has an additive inverse. Finite, like finite. Finite subspaces have additive inverses. All right, in 2 minutes, after thinking about this for another 2 minutes, I'm going to Google and just educate myself. Let's see. Finite subs like any singleton is not a subspace, QDoc. Only the zero vector singleton is a subspace. Only the zero vector. The zero vector is the only singleton subspace. I mean, for infinite fields, every subspace is infinite because of closure under addition and scaling. Now, the subspaces of finite fields could have additive inverses. Like, let's think about Z2. You know what I'm saying? Z mod 2 subspaces of Z mod 2 to the n or something. Let's look at the special case of Z mod 2 to the 1. I mean, how would you get a subspace of... Here, it would have to be Z mod 2 to the n. Let's say Z mod 2 cubed. You know what? Let's just say Z mod 2 squared. Ba-da-ba-ba-ba-da. Zero, 0, and 0, 1 are in the subspaces of Z mod 2 squared. minus 0, 0, 0, 1 equals 0, 0, 0, 1. Because minus 1 mod 2 equals 1. I mean, the additive inverse of u is u in this case. So, like, so that actually does not form, that's actually not the additive inverse. So yeah, the additive inverse of u is not u in that case. Beep 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 beep. Beep 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 beep. Beep 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 beep. All right. Let's go to like Math Overflow or something. Oops, clicked the wrong thing. Which subspaces have additive inverses? Oh, there's a solution. Look, this solution is the same as my solution. So my guess was that that the singleton 0 was the only one. That the singleton 0 is the only one. Let's see what people are saying. Why? But why is this the solution? You know what? We're gonna have to formalize this. We have to formalize it because ba-da-ba-ba-da-ba. Ba-da-ba-ba-da-ba. Yeah, so we're gonna do this by associativity. 18. Very interesting to formalize. So yeah, this rando on Math Overflow had the same answer as me. All right. All right, so we're talking. What are we talking about again? Oh, yeah. We're talking about U1, U2, W is in the subspaces of V. Suppose U1 plus W equals U2 plus W. Want to show U1 equals U2. Left side equals U1. U1 equals U1 plus the set containing 0. Ah! Associativity will not work because I cannot do this. Because this does not hold. So this is going to be very interesting. You can't cancel. But what you can do is dig down into the set. And then this is going to be U1 plus W minus W. U1 in U1, W in W. And this is going to be U1 plus W minus W, U1 in U1, W in W. And this is going to be U1 plus W minus W at the set level. Now we have a hypothesis. We can just rewrite that hypothesis. Just rewrite that hypothesis. Go back into the set. Y'all, this doesn't work. One of these steps is invalid. I'd rather wrestle with it in formalization. I'd rather wrestle with it when I formalize. All right, the last four I think are all direct sum. That's good because direct sum is the concept I'm like least familiar with. And we've been at it close to an hour, so if I can do 4 exercises in 2 hours, I'll be really happy. All right, we're talking x, y, x plus y, x minus y, 2x. Want to find W in subspaces of F5. ST U direct sum W equals F5. Let's go back to the definition of direct sum. The only way to write 0 is for each uj to be equal 0. Let W equal the set W1, W2, W3, W4, W5 in F5 such that WK is in F. You didn't go over this in the book, I don't think. X plus W1, Y plus W1, X plus Y plus W1, X minus Y plus, no, sorry, 2, 3, 4, 2X plus W5. Now, minus X minus Y minus X minus Y minus X plus Y minus 2X is in if minus X minus Y minus X minus Y minus X plus Y minus 2X is in W, then U plus W is not a direct sum. So to find a way to guarantee a way to guarantee that this vector won't be in U, is it enough to just say that like U is equal to like yeah, it is enough. It is enough to say that. So let W equal W1, W1, W2, W2, W3, WK, and F. We're just trying to find any direct sum, then we'll worry about this condition that we actually want to find. Is a direct sum and written the direct sum W. That's W2 and that's W3. So now I need to figure out a way to make a subspace that to make a subspace where the direct sum is the whole. Or let W equal W1 plus W2, W1 minus W2, W1, W2, 2W1. That would not form a direct sum. Now, if we did it like this, W1, W4, that would still not equal the whole set. You need these two to be the same so that you force x plus y to equal x minus y. Want to force x plus y equals x minus y. Okay, so this is like really obvious, right? If I had u x0, x in R, v 0y, y in R, then u plus v would be a direct sum and it would equal R2. But in the case where u is x, y, x plus y, x minus y, 2x, I don't really know an analogy. Okay, let's think of this intersection is the singleton zero. Let's think of that as our frame of reference. So proof. First, suppose that u plus w is a direct sum. If v and u intersect w, then v minus v equals 0, where v and u and minus v and w. By the unique representation of 0 as a sum of vector and sum of u and blah, 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 we have v and w. Thus, we have v equals 0. Thus, u intersect v equals singleton 0. This is extremely difficult. I don't know if there's a proof that a counterexample doesn't exist. Like, what would that proof look like? I've been cooking on this for like over 20 minutes. Let me stretch a little bit. My back feels a little bit better because the ibuprofen kicked in. XY, x plus y, x minus y, 2x. Another subspace of V. All right. Oh, that was 21. Oh. Yo, I skipped to 21. 20 is the same thing but easier. So let's look at 20. I don't know if I'm going to want to formalize these ones, y'all. I don't think we're going to want to formalize them. Okay, so this is going to be easier, I think. This is going to be W1, W2, W2, W3 in F4 such that W1, W2, W3 is in F. Am I right? Did I spend 30 minutes on 21? I feel like this got knocked out really quickly, and I think it's right. So, oh, this isn't right. This isn't right. You know why? Because let 1111 in W. And what this is going to do is going to violate that the intersection is 0 and 1111 in U. Then U intersect W does not equal the singleton 0. So U plus W is not a direct sum. What would the other proof look like? If we were proving it, it would be that x plus w1 equals 0, x plus w1, x plus w2, y plus w2, y plus w3 equals 0. Implies x equals 0, y equals 0, w1, w2, w3 equals 0. Let x equal 1, w equal minus 1, y equal 1, w2 equal minus 1, w3 equal minus 1. Yeah, so that's not a direct sum. It is the whole set, though. It is the whole set F4. It is the whole set F4, but it's not a direct sum. Ooh, back still hurts. Ugh. The ibuprofen feels good though. I'll give you that. I'm gonna snack. I have these chips that the Korean place gives. Whenever you get takeout at this Korean place, they give you these like snacks. All right, I feel like I'm being trolled here. I don't think we're gonna prove that it can't be done. I don't think that's the object. I think the object is to find the subspace W. I am spinning my wheels on this. What are we even doing here? X, X, Y, Y. It has to equal the whole space. it has to equal the whole space, but it has to be a direct sum. Can be written in only one way, as a sum. Now I'm like 20 minutes on this one. Y'all, I can't do this. I wonder what's next. Oh, really? 3 sub 22 is even harder than 21. Y'all, I want to pivot to code, y'all. Maybe I'm just not trying hard enough. Oh. Oh. Oh, yeah. I'm using the back of the chair to massage my back. Oh, yeah. Oh. Okay. Feels a little better. I'm thinking in my head. I'm sorry I'm not like being a very entertaining streamer today. I'm literally like trying to find vectors W, and I keep trying them out in my head, and they just don't work. Hold on, hold on, hold on. Is the singleton 0 valid? No, because that doesn't. But watch this. Zeros. Y'all, I should have thought of this earlier. W1, 0, 0, W2 in F4 such that W1, W2 in F. Equals X plus W1, X, Y, Y plus W2 in F4. Such that X, Y, W1, W2 is in F. This is amazing. Y'all, I think I got the winner. Um, yep. Hold on. Does U intersect W equal the 0 singleton? Let PQRS in U intersect W. Then PQRS is in U and PQRS is in W. This means P equals Q and R equals S. And this means Q equals 0 and R equals 0. And when you put all that together, you get PQRS equals 0, 0, 0, 0. Therefore, U intersect W equals. Y'all, we did it! We freaking did it. Hold on, we still have to prove that it forms the whole set. I despaired. I spun my wheels for close to 30 minutes, and I despaired. But you know what? I got it, okay? I got it. That's what we're talking about here. This is the linear algebra done right stream. It's what we do. It's what we do. So next I have to show that U direct sum, which I already proved, W equals F to the 4. I see it. Let's do two subsets. U plus W is intersect F4. And F4 is a subset of U1 plus direct plus W. P in U plus W. Oh, you know what? I'm going to do PQRS in U plus W. Then there exists X, Y, W1, W2 in F such that PQRS equals X plus W1 X, Y, Y plus W2. I don't know how to show this. P equals X plus W1, Q equals X, R equals Y, S equals Y plus W2. Hold on, this might not be the whole set. This might not be F4. S equals R plus W2. P equals Q plus W1. Q equals X, R equals Y. And R equals S minus W2. Now I'm nervous. I'm nervous that I'm wrong. I'm nervous that I'm wrong, y'all. But you know what? I'm going to jump into the restroom. I'll be right back. So, this is really has two parameters. Now, two parameters can't cover the whole set. How can we show we want to show that PQRS is in F4 is in F4 because we're just doing the first direction of the equality. So we're doing the mutual subset definition of set equality. But wait, is this just simple? Is this just that x plus w1 is in F and x is in F and y is in F and y plus w2 is in F? I'm thinking about this all wrong. I feel like it has something to do with span. I literally feel like it has something to do with span, but it's at a part of the book before span is gone over. So, like, what do you think he wants? Do you think he wants a span-based proof? Are we just supposed to struggle with this and fail and then wait until later in the book when span is introduced and then be able to do it? I don't know like what methodologies he goes about using span. So we can set it up like this. We can do like an augmented matrix. One, zero, 1, 0. X, Y, W1, W2 equals P, Q, R, S. The next one is x equals q. So that's 1, 0, 0, 0. The next one is r equals y. So that's 0, 1, 0, 0. And the next is 0, 1, 0, 1. Okay, so we're running out of room. R1 replaced with R1 minus R2, and R4 replaced with R4 minus R3. So that's 0, 0, 1, 0, P minus Q, pipe. It's 1, 0, 0, 0, Q, 0, 1, 0, 0, R, and 0, 0, 0, 1, S minus R. And this is just going to be a column interchange. It's going to be 1, 0, 0, 0, pipe Q. The next column is going to be 0, 1, 0, 0, pipe R. The next column is going to be 0, 0, 1, 0, pipe P minus Q. And the next column is going to be 0, 0, 0, 1, S minus R. So in conclusion, X equals Q, as we knew. Oh no, this was a roundabout way of saying the same thing that I already said. Y equals R, W1 equals P minus Q, and W2 equals S minus R. Which I do not think constitutes the whole set. Yeah, this was just a different way of writing the same thing. So what this means X equals Q, Y equals R. P minus Q, S minus R. That means X, Y, W1, W2 equals no constants plus P times 0, 0, 1, 0 plus Q times 1, 0, minus 1, 0 plus R times 0, 1, 0, minus 1 plus S times 0, 0, 0, 1. Which reminds me of this. Linear span of 0, 0, 1, 0 1, 0, minus 1, 0. 0, 1, minus 1, 0, 1, 0, minus 1. 0, 0, 0, 1. The question is does this form a basis? Why not Prolog? Because I write a lot of cock and I prefer that language. I actually don't know any Prolog. I literally don't know Prolog. Like difference between cock and Prolog. Prolog isn't like a type theory, it's logic programming. What is the difference between proof assistance and logic programming? They're both related. There's little overlap in practice. Logic languages like Prolog use a programming model based on backtracking search. You express your problem as a set of constraints and it gets executed as the language searches through possible solutions to these constraints. This makes side effects really awkward. Backtracking in logic programming underlies the computation the way function application and simplification do in functional programming, and step-by-step execution of statements does in imperative programming. Okay, so this idea of backtracking is like what logic programming is all about. So logic programming is an extension of like a SAT solver. This is a good article. I just like type systems. I like lambdas. I like functions. You know what I mean? But today, what I'm doing is I'm actually not writing cock. I'm working on exercises from the book in pen and paper. But do you write Prolog? Jack Frosler, do you write Prolog or something? All right, I'm going to read ahead to bases. I'm going to read ahead to bases in the book to see if he gives a proof strategy. Span is the smallest containing subspace. I'm just reading ahead. These vectors are linearly independent because it's a perfect row reduction solution. I think you can represent every point. I really think every point is representable. I just can't, like, prove it. Basis. Yeah, linearly independent in spans, right? Well, we know it's linearly independent. How do we know if it spans? I need more proof strategies to show that a list of vectors spans. Does it span V? I'm just going to go with yes and call it a day on this. Because I still have to prove the other side. F4. So we have PQRS in F4. Want to show that there exists an XY W1, W2 in F4 such that P equals X plus W1, Q equals X, Y X, R equals Y, S equals Y plus W2. Is this sort of the idea? I'm calling this checked off. I feel like I'm lazy, but I'm like willing to call both sides checked off. I'm only going to call both sides checked off, you know? Because I showed that it forms a point. When I did row reduction. I don't know about this, y'all. I'm very sure that it forms a direct sum with you, but not sure enough that the sum equals the whole space. Let me read if it says anything. When a sum equals the whole space. Where each element of the sum can be written in only one way. All right, let's move on from 20. Let's move on from 20. U equals x, y, x plus y, x minus y, 2x. In F5 such that x, y is in F. This is a struggle, y'all. We are struggling. This is really a struggle. Well, W can equal 0, 0, W1, W2, W3. Wrong again. Let's try this. W1, W2, 0. in F5 such that W1, W2 is in F. Now let W1 equal 2, W2 equals 0. Then 1, 1, 2, 0, 2 is in U, and 0, 0, 1, 1, 0, 0, 0, 2, 0, 0 is in W. The intersection could still be empty. I mean, did I say empty? The intersection could be the 0 vector. I feel like we got this. All right. U intersect W is the set containing 0. Premise. V is in U intersect W. Therefore, V is in U and V is in W. Therefore, there exists XY such that V equals XY, X plus Y, X minus Y, 2X. x equals 0, y equals 0, x plus y equals w1, x minus y equals w2, 2x equals 0. But this becomes x, y, w1, w2 equals 0, 0, 0, 0. V equals 0, 0, 0, 0, 0. Therefore, U intersects W equals so we've proven that it's a direct sum. I provided that W equals 0, 0, W1, W2, 0. And I'm very sure that it forms a direct sum with U. But let's see if the direct sum equals the whole space. In F. This is clearly a subset of F5. Let V in F5. So yeah, U direct sum W is clearly a subset of F5. Now we have to show that F5 is a subset of U direct sum W. which I feel like looks something like this. No. This is awful. Y'all, I can't do this. It's nasty. This is a nasty exercise. It's not obvious. Okay, so 24, it's not clear to me that it's true. Because how can that be? How can a linear, I mean, it's not a linear combination, but how can a combination of odd and even functions turn into the whole function space? Because what about functions that are neither even nor odd? Are you saying that functions that aren't even or odd, that are neither even nor odd, I should say, can be expressed as a sum of an even and an odd function? I'm not good at this. I'm clearly not good at math. I had some W's, right? Like I had 15, like I feel like 15, 16, 17 were all really good. I had some wins, but I only got 15 minutes left. I'm just gonna do some reading, I guess. Let's review our standing assumptions. Notation: F denotes R or C. V denotes a vector space over F. In the last chapter, we learned about vector spaces. Linear algebra focuses not on arbitrary vector spaces, but on finite dimensional vector spaces, which we introduce in this chapter. Span and linear independence. We have been writing lists of numbers surrounded by parentheses. We will continue to do so for elements of f to the n. So for example, 2 minus 7, 8 is in f to the third. However, now we need to consider the lists of vectors which may be elements of f to the n or of other vector spaces. To avoid confusions, we will usually write lists of vectors without surrounding parentheses. For example, blah 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 is a list of length 2 vectors. Is a list of length 2 of vectors in R3. Notation. We will usually write lists of vectors without surrounding parentheses. Linear combinations and span. Adding up scalar multiples of vectors in a list give what is called linear combination of the list. Here is the formal definition. A linear combination of a list, v1 to vm, of vectors in V is a vector of the form av1 plus dot dot plus amvm, where a1 to am are in F. For example, 17 minus 4, 2 is a combination of 2, 1 minus 3 and 1 minus 2, 4, because 17 minus 4, 2 equals 6 times 2, 1 minus 3 plus 5 times 1 minus 2, 4. 17 minus 4, 5 is not a linear combination of the same list because there do not exist numbers a1, a2, and f such that blah blah blah. In other words, the system of equations 17 equals 2a1 plus a2, minus 4 equals a1 minus a2, and 5 equals minus 3a1 plus 4a2 has no solutions, as you should verify. I'll verify that when I'm reading this for real. I'm just doing a pre-read in my last 10 minutes. The set of all linear combinations of a list of vectors v1 to vm and v is called the span of v1 to vm, denoted span of v1 to vm. In other words, span of v1 to vm equals a1 v1 plus dot dot plus am vm for all a1 to am in F. The span of the empty list is defined to be 0. This is the singleton 0. The previous example shows that 17 minus 4, 2 is in the span of these two vectors, but 17 minus 4, 5 is not in the span of the same vectors. Some mathematicians use the term linear span, which means the same thing as span. 2.7, span is the smallest containing subspace. The span of a list of vectors in V is the smallest subspace of V containing all the vectors in the list. Suppose v1 to vm is a list of vectors in V. First, we show that span of v1 to vm is a subspace of V. The additive identity is in span of v1 to vm because 0 equals 0 times v1 plus dot dot plus 0 times vm. Also, span of v1 to vm is closed under addition because yada yada. Furthermore, span is closed under scalar multiplication. Okay, so it's a subspace of V. Now we have to show that it's the smallest subspace of V. Each Vj is a linear combination of V1 to Vm. To show this, set Aj equals 1, let the other a's in 2.3 equal 0. What do you mean in 2.3? Yeah. Conversely, because subspaces are closed under scalar multiplication and addition, every subspace of V containing Vj contains span of V1, containing each Vj contains span of V1. Yep, it does. Thus, span is the smallest subspace of V containing all the vectors. I'm not sure if that holds. show that the standard basis spans f to the n. Here, the jth vector in the list above is the n tuple with 1 in the jth slot and 0 in all other slots. Suppose x1 dot dot xn is in Fn. Then, x1 dot dot xn equals, clearly, x1 times the first standard basis vector, x plus s2 times the second standard basis vector, etc. Thus, x1 dot dot xn is in span of blah 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 as desired. Now we can make one of the key definitions in linear algebra. A vector space is called finite dimensional if some list of vectors in it spans the space. If some finite list of vectors in it spans the space, we should say. Recall that by definition, every list has finite length. Example 2.9 above shows that f to the n is a finite dimensional vector space for every positive integer n. The definition of a polynomial is no doubt already familiar to you. A function p from f into f is called a polynomial with coefficients in f if there exists a0 through am in f such that a0 plus a1z plus a2z squared plus dot dot plus amz to the m for all z in f. P of f is a set of all polynomials with coefficients in f. With the usual operations of addition and scalar multiplication, P of f is a vector space over of f, as you should verify. In other words, P of f is a subspace of f to the f, the vector space of functions from f to the f. If a polynomial is thought of as a function from f to f is represented by two sets of coefficients, then subtracting one representation of the polynomial from the other produces a polynomial that is identically zero as a function on f, and hence has all zero coefficients. If you are unfamiliar with this fact, just believe it for now. We will prove it later in 4.7. Conclusion: the coefficients of a polynomial are uniquely determined by the polynomial. Thus, the next definition uniquely defines the degree of a polynomial. I might call it 5 minutes early. 4 minutes early. Because I don't know how much I'm getting out of reading this. I'll just skip this part about polynomials because I'll come back to it later. I can't believe that r to the r equals the direct sum of the even functions and the odd functions. That to me is bizarre. Is very bizarre. And you know what? It's been enough hours, I think, that I should have more ibuprofen. Or no, I should probably wait one more hour. $22 is gonna be really hard. I'm gonna code next session. I might have to come back to these exercises while I'm like formalizing and do another pen and paper session. But I want to like make some progress on formalizing subspaces. So next time, that's what I'm gonna do. unable to locate library classes, which is annoying because I definitely compiled it. It definitely has a .vos file. But yeah, I'm going to make some progress on formalizing subspaces. I'm going to make a file called debt. No, I'm going to do that later. Yeah, actually writing code is going to be nice again. All right, page 44 of 352. 300 pages to go, baby. All right, I'm going to stop stream. Had enough for today. My back still hurts. I have some stuff I got to do. So, sorry we didn't finish those proofs, y'all.